in on a long-standing problem called quantum mechanics. It's really a paradox system where the paradox shows up in several forms, but the easiest way perhaps to state what the paradox is simply the wave-particle duality. This turns out to be extremely profound. I would have to say that's probably no surprise to you that the fact that in the universe are two different forms, we could say, of energy, and we'll just put it that way for now, but we actually need to understand the quantum paradox. I've been over in the past couple of lectures what is a paradox and what constitutes the paradox in this case. But if it were possible to fully state what the paradox is, it would no longer be a paradox. There would be some kind of relationship where there's a contradiction, in which case you have a contradiction. But a paradox can be a contradiction, but it also can be superposition. Two forms of an inability in us, an inability perhaps in our mathematics, perhaps in some aspect of what we're doing we haven't fully comprehended, but this forms a very interesting edge where humans are just, I'm speaking myself included, we're just fatally attracted to this kind of a thing to try our hand at making sense out of it. So that's led to some pretty amazing theories, including the many worlds theory, which if you're not fully, you're not sure what the many worlds theory is, because it certainly sounds kind of strange, doesn't it? Well, why would physicists or anybody, with intelligence talk about something of that sounds like, what do you mean, many worlds? First of all, world is kind of an abstraction of the earth, right? I think of it as the earth of humans. It's that's what we call the world. We're on earth, but we're in the world, and that's kind of I guess you'd say, the religious or scriptural, or as I prefer to say, philosophical way to say it. Well, the world is certainly a topic of philosophical consideration, which makes it interesting since you're in it. So it's an involution problem in some sense to get a grip on reality. And we all know about that, so let's get into our topic today. I want to show you a couple of things. You may see over here I have something prepared. I composed this morning because I've been thinking about this day and night. So I'm just going to show this to you. You could capture this on your screen in some way. And excuse me, I'm not too good at doing this, pretty obviously. There. This takes the place of the technology that I probably should have to be a YouTube presenter. So we're going to cover that. And we're going to try to make some very, very simple relationships. Not make them up, but essentially discover them. We want to discover, if we can, a relationship between the wave form of energy and the particle form, which makes the wave-particle duality. Why? Why is that a paradox? Essentially, it's because a thing, and we have to use the full abstraction now, there are two things which cannot coexist in the same instant of phenomenalization, which is a fancy-dancy way of saying that we can only measure particles. Now you may say, well, we certainly can measure waves in some sense. That is correct, but it's a different form of measurement because it's not strictly positional. Now obviously there's a relationship, even in a wave, to position. You could say positionality, and that's a helpful word. I just thought it up just now, that just came out. Positionality would be a characteristic of how we apply mathematics, which becomes extremely profound when you consider the absolute basics of what you're doing with numbers. Numbers, of course, have been treated philosophically since the beginning of time, since they're somewhat magical, you'd have to say. But what are they? Well, that has been difficult to say as well, but I have, with the help of John Horton Conway, an absolute definition of what the number is. Has a direct impact or influence or relationship to the quantum paradox. Because let me state what the quantum paradox is in terms of measurements. That is how we actually directly observe what's called generally the universe, but in this case is subatomic particles. And you actually have to say particle. This is one reason for the standard model of particle physics, which starts out with the outlandish, actually anti-scientific, axiomatic premise that's not questioned, that everything in the universe is a particle. Well, the only way to explain how physics is able to use such a ridiculous axiomatic basis, because that's totally anti-scientific, not totally. It's a concession to the fact that we can only measure particles at this level, which is the edge level. And that's what we want to get to, is the edge. To see what we can say about the edge. And this is the inner edge. Now, you can try to conceive that in your mind as a series of concentric circles that collapse to a point where we have trouble is at the final collapse to the point, which is an infinitesimal jump. It's actually a quantum jump in circular space to get to what we would ordinarily conceive as zero. Now, it turns out it's very difficult to find zero in the physical universe. And so the positionality of how we use numbers, how we employ mathematics, is strictly linear. It's a linear anything. Anything that we measure has to be on a line, or we can't measure it because our numbers are all on a line. Now, you may intuit that it would help if we had a different number system. That's there's actually a serious contradiction, not really even a paradox, although it could be a paradox if you can deduce it to be such. But if you're measuring on a straight line, you're using linear numbers because it starts at 0 and goes to 1 to get the index. That's a straight line distance. We accept this so viscerally. I've stated, this must be blueprinted into us. Well, that's hard to deny, because the results of using linear geometry is what it is, and then linear mathematics, which is where we get the term linear algebra, it's all referring to straight line distance, and it's always distance, although you could make an analog for time, and that has been done, or we would not have a discrete value for light speed, which is a proportional number. It's the relationship between distance and which we conceive of as distance in space. So you could say it's a space-time relationship. Well, Albert Einstein certainly proved that it is an actual physical relationship between two linear numbers. But the problem is, and this is how we're going to introduce this topic today, so you know ahead of time what the goal is. We're going to find out that time, although it is linear the way we conceive it, it's referring to a phenomenon that is not linear. Now, that is also true in space, but only when you conceive space the way the universe conceives space. We do not conceive space the way the universe does because we want to use numbers. And therefore we make a grid. And I've said this so many times, I'm sure you're well acquainted with the fact that science, including Einstein's science, was based on a 3D grid called cubic space. But physics discovered in the 20th century irrefutable cumulative proof that the universe is not based on linear logic exclusively. You'd have to say that it is, in some sense, it is in a derivative sense. And that's why we can compose distances to stars, which is a straight line distance, but using a phenomenon called light, which is not strictly speaking a straight line distance. And so the question we want to answer is, where do we get the linearity out of light propagation? We think we know, but now we actually have to be sure we know, because this actually is the heart of the paradox. So to sum all this up, to get going, I'm going to show you some material here in a moment. It's very simple material, but what is it that I mean by positionality as a valid reference frame for what we're going to be talking about? Don't we all take this for granted, that we use a grid to compute spatial distance? Yes, we do. And that's why we need calculus. So there's one aspect of it. Calculus is used to get at curvature. That's how we all learn it. You draw a curve and try to compute basically the infinitesimal of the curve. And then you get to integral calculus, which is the inverse. But it's all quite simple when you state it. When you go to do it, it sure seems convolute, when actually the circle is quite a simple object to comprehend mathematically, but not with linear numbers. If you use linear numbers, you're going to need 2 to even state anything about the circle. If it's a sphere, we use 3 numbers, because that is full volume space, and the universe uses spherical volume space at all scales. Everything is spherical, from the proton to the atom. Now, when you get to the molecular level, you have more structure, obviously, but it's the structuring of very tiny spheres. And the 2 main ones, well, you would have to say 3, are the proton, the center of the atom, the electron, which makes shells around the protonic core, and the photon, which is a free flight particle, which is actually, to state the paradox itself, it's a free flight particle. That's actually not true, unless you can state the nature of the particle as it propagates as a wave, and you can't, because it can't be both at the same time. And so the wave-particle duality appears to be a contradiction. What we need to do now is prove that it is not a contradiction, and that will solve the quantum paradox at all scales, at all levels. That is not really scale, it's all at the subatomic scale. Now, in the case of entanglement, the most difficult of all the quantum paradox manifestations to explain, and the one that just drove Albert Einstein really up the proverbial wall, that has seemingly been solved, and it's widely acclaimed that controversy that Einstein started with Bohr, that has persisted to this day in some form, is kind of like the validation of the Big Bang. Over the past it's been more than 70 years that we've had this paradox. The wave-particle duality and entanglement and superposition and the collapse of the wave function, Schrödinger's cat problem, everything is involved in this one paradox that we cannot reconcile the form of the wave with the form of the particle. And it goes right down to philosophy. You actually have to take, either retroactively or to begin with, somehow you're going to have to address the philosophical disparity between the formulation of the universe in terms of particles, which are the only things we can directly measure, either to get position or momentum. You need a particle to do that, because a wave has neither, although there's a footnote. And there's always going to be a footnote in everything you say about quantum mechanics until you solve the paradox. That will roll everything up. And the way to get at that is hyperspace. But there's another problem with the term hyperspace. It's already been used. Because we started out with a 3-line system, cubic space, when you add a 4th line, that by convention is called hyperspace. So we need to distinguish between 2 kinds of hyperspace, because the universe is not made of cubes. It actually operates on a completely different geometric and mathematical basis, although in the case of mathematics, not quite, and therefore, in the case of geometry, not quite either. And there's always a footnote to anything you say. No matter how you try to state this paradox, there's going to be a footnote that you'll have to address and which you can't, because it will lead right back to the paradox that you can't solve, which is that a wave is not a particle, and a particle is not a wave. However, that might not be true. In fact, in the case of the electron, not the proton, but the electron, that appears to us, the fermion electron, rather than being a particle, you would have to say, or you could say, that it's a particle because it has locality. But it doesn't have a distinct surface, not in the same sense that a proton does. We can see the distinct presence of the proton because of the way the electrons occupy the space force shells around it. And so the electron is completely different from the proton for that reason, is that the proton is always at the center. So it exerts a spherical force field from a center. The electron, it can be said to be a particle because it also has locality, but it doesn't manifest its locality by a force field in that sense. It doesn't have that kind of a boundary. What kind of a boundary does it have? It has a boundary that's in another dimension. And that's not quite accurate to say either, and we're going to straighten all that out today with the introduction of a new term called a domain. This term has been used even of space and time, and we are talking about space and time, but we're going to have to unravel what space and time are. We're going to have to take them out of Einstein's formulation, although it works. So we're going to use Einstein's formulation of the relationship between space and time, which is a geometric and numeric relationship that works. So Einstein achieved something that's incredibly profound. But we do have to take it apart because he directly related space with time. I'm going to show you today that that is incorrect. And here you're going to see a very simple diagram of a circle. You can disregard the caption to the left and just look at the circle and disregard the square boundary and look at the lines. There are 8 of those lines. The number of lines does not matter. They're indicative of one line, but it's not a linear line. It is a circular line, and that needs to be disambiguated because a circular line would curve, and none of these lines indicated by the 8 arrows are curved lines. And you should never say curved line, because a line by definition is straight. This is simply a convention that we need to decide how to refer to a line. Can you say a curved line? You could, and we do, and I might, but it'll be by accident because I'm trying to make sure that we distinguish between a line and a curve, because they're not the same. They're quite different. Anything that curves is not a line. However, you'll see this is a curved surface called a circle. That is the normalized condition of a curved line in 2D space, is that it's a circle. If it were imbalanced in any way, well, I won't say in any way, but if it were imbalanced, it would be an ellipse. The typical flight of a planet around a star is an ellipse. It's very interesting, but it's a variation on the circle. How can you say that and know that you're saying it correctly? They're closed lines. And it sounds like you're saying clothesline, like you're hanging out your wet laundry to dry on a clothesline. I'm sorry about that. I didn't invent that pun. It just comes up. But a closed line. And that's a family of curves whose most normalized form is the circle. Now in volume space, that's a sphere, obviously. And that's why we get the term unit circle and unit sphere, is when you assign a radius of 1, that's a magic number. And that really helps us formulate how to use the Pythagorean theorem on a circle and extend it to a sphere, to use our linear number system and our linear geometry to get a curvature. But the circle is a closed line, because a regular line is not closed. It goes to two polar infinities, or you could say antipodes, antipodal points, which are simply in opposite linear valent directions called plus and minus. That's how we designate a 180-degree orientation between the direction of the two rays of the line. Now we generally unify that into one complete line, which does go off to two infinities, but just overlooking that for the moment, you do have an Archimedean center. That's a balanced center. And then we have to give it a number that's peculiar, because it's the central number. It's not +1, and it's not -1. Now in distance, we use +1 as the index, and that's the index of linear space for linear spatial separation. It's from 0 to 1. But what is 0? It's a very strange number, isn't it? And you can find at least one reason in your mind instantly, certainly if you're a mathematician, but really if you've been to grade school, you know why 0 is peculiar. It's because of division. And that's not its only peculiarity, but that's its major one, because you can never divide by 0. Do you know why? No one else does either. That's never been answered, is why can you not divide by 0? Well, you can imagine, even if you haven't been exposed to an attempted explanation for why 0 does not behave as a linear number at all, but it does. And I'm not going to tell you what the speculative answers are for why 0 does not work for division. You can certainly find out in the IEEE documentation for computer technology that if you send a division by 0 instruction to a CPU, it locks the CPU and you have to reboot. So it's a physical, the universe declares that you can't divide by 0. Well, that invalidates the linear number system for division. Obviously, that hasn't stopped us, but in learning algebra and higher forms of linear mathematics, such as calculus, you're always just tiptoeing around 0, because 0 destroys most advanced calculations. And the reason is, I'll just tell you so you have a conceptualization if you haven't figured it out already, it's a linear infinity. And that's profound. So that's just background information, and that's our first diagram. I want to show you another diagram now that's equally simple. And this is, again, just a plain circle. The simplest of all the closed lines. Now, not all curves are closed. The hyperbolic family of curved lines, we'll have to say it that way, I really can't get around it. The hyperbolic family of curved lines on which space-time is based is a family of curved lines that don't close. Their endpoints still go to infinity, but not in polar opposite directions. And so if you can see this, here's a straight line, but if you say these are the 2 points at infinity, which obviously I couldn't actually stretch my arms that far, but where the contact is with infinity, you can take an integral so that you can narrow the range, so you can get an equation of curvature. And this can be done with calculus, but essentially I just looked up the word, the eccentricity. The eccentricity of the curvature is gradual to a limit. So even though it's not closing, it's still going to 2 infinities. The infinities are the places where the endpoints of the curved line disappear are not polar opposite. They're both in the same, in this case, vertical direction. All right, so you do have to, so we just use 2D for now, but this also applies in volume space. which is the right way to say 3D space, because it's not 3D. It's only 3D in our mathematical system. The universe does not respond to our 3D grid, not at the two limits. And we're going to find out why. But the eccentricity goes up and up and up until it achieves a specific limit called the parabola. And in volume space, that would be a paraboloid, if one can imagine such a thing. And mathematicians enjoy imagining such things. Quite helpful if you can imagine it. So it curves up and up and up, and it's still hyperbolic until it, in the vertical orientation, the vertical way that it's curving, it achieves a parabola, which is basically a balance line. Because after the parabola, an infinitesimal more past the parabola, and it goes vertical. And so what happens to the hyperbola, which just at that instant, you could say instantaneous moment of space in the projection, it achieves this, and that's called a parabola, because it has actually a different equation than the entire family of hyperbole, but it's only at that limit that it achieves parabolicity. The parabola is very useful on Earth for firing like cannonballs, because, well, I think you know why. That's a parabolic curve. The trajectory of a cannonball that's fired at an angle up will go up and achieve a parabolic curve at the top and come down exactly symmetrical on the other side, except for air resistance. And there are other factors, such as there are other factors that are minute and basically incomputable, like the effect of gravity is not completely uniform throughout that. Perhaps it might even be. But that's the nature of the parabola. It's a unique curve. But after the parabola, which is fixed, if it goes up any more, the endpoints go up any more, they go vertical. In other words, it's asymptotic. The two ends of the parabola are now asymptotic to verticality. So any further increase would close the asymptote. So they would actually hit infinity, but going vertical, it has to be the same infinity, and that's the closure. And now the horizontal line has been completely transformed into a vertical line. So that's the family of curves. It's considered to be three families: the ellipses, the hyperbole, and the parabola. But you can see the parabola is not a family. So there are only two families of curves: the hyperbole and the ellipses. The normalization of a hyperbola is not the circle. It's really an inversion on the relationship between vertical and horizontal. You can do that with two numbers, and that's how all curves are composed in 2D, is on two numbers, but the relationship between the two numbers can be, in this case, inverted. Normally we try to get the function of a circle, but if you get the function of a hyperbola, you get Einsteinian spacetime, which is meant to describe sphericity, because gravity is a spherical function. But we don't know how to do that. We literally don't know how to do that. I do. So these two circles, I want you to just consider a very simple proposition. That in the first one, you have a dotted line on the outside of the circle, but everything inside the dotted line is colored. In the second one, you have a dotted line, and everything inside of it is a different color, which you could think of as the opposite color. these representing black and white perhaps. And the dotted line I want you to think of as a force field. And so what's the difference between these two in terms of their color valence? The first one I want you to think of as gravity, so that the dotted line represents a radius of gravity. And you could think of that as being around the Earth. We'll use the Earth as a typical example of a center of gravity. That would be the blue circle is the surface of the Earth. The dotted line is a concentric circle. That is a parallel closed line in circular space. That outer circle that's a dotted line is parallel in circular space to the inner circle, and I think that should make sense. There obviously is a mathematical difference, though. It's not, strictly speaking, parallelity as we learn it with two straight lines that are parallel. This is an analog, but you have to be cautious with analogs here. So that is an example of a centripetal force line. In other words, the Earth is not blowing off light. The sun is. The sun has something coming out of its surface. Basically, light. We just think of that aspect of it. So something is coming. Well, that's the second circle. And that's why it's white, is because it's showing centrifugal force. And those are the only two forces that balance in circular space. And that brings up the concept of a different kind of straight line. Now, we've already talked about the conventional system of referring to a line, that I say that should always be a straight line when you say line. But we don't have a word for a curve that's equivalent to the word line, unless you want to adopt the word curve. So let's do so now. The curve, that is the sun, which then has a center. It's a curve with a center. We call it a circle. You could think of it as a sphere, because of course the sun is a sphere. But we're looking at a flattened version of that, which is exactly how the sun looks to us. Well, let's just say the moon in this case. When you look at the moon, you don't see a sphere, unless you want to defy what you're actually seeing, which is a circle. We don't see spheres. We see circles. But we can easily, I'll just say with a certain initial effort, which then we get used to, when you look at the moon, you realize you're seeing a sphere, even though that's not what is registered in your brain. It's not what's registered in your mind. So which is to say that this is a reasonable projection. And you don't need to keep switching, just accept what you're seeing, because the circle and the sphere are extremely closely related. Now, in the case of B, that is the second circle, you're seeing centrifugal force represented as the dotted line above the surface of the sun is a centrifugal curve. So that's the curve of centrifugality. In terms of light, that's how light goes out from the sun. When you integrate the whole thing, you're looking at the whole thing at once. It's all coming out as one line. It's coming out in a straight line. In any direction from the center, it's a straight line going out. And that's how it goes out on a straight line. So there's the linearity that's embedded in the circularity. It's also embedded in sphericity, as I proved in 2022. I believe it's the first time that's ever been proved, possibly because no one ever thought it needed to be proved. Because that is how we see distance to stars, as on a straight line. But you can see that straight line is one of an integral line. That all the lines coming out, and let me just switch back real quickly here so you can see why I showed you this one first. Those 8 arrows are 8 of the integral line, which is difficult to say grammatically correctly, but I think you got the idea. I hope so. It's very simple, but these are the two forces that exist in spherical space. They're called centrifugal force and centripetal force. So, now I'd like to show you something else. And this is a document that I composed yesterday. And I'm just going to read from it, but I want you to see it so that if you wish, you can capture the page. And I'll be switching pages as I read through this. This won't take too long, but I'll be annotating this. This is late breaking stuff. This is the stuff that I've been thinking about recently because I'm not done. Although I've already achieved new thresholds, several new thresholds that are beyond the current level of physics. That hasn't been proved because only consensual science can prove that, such that I could state it to you with a straight face. What I can say with a straight face is that I know it. So that, I know, but that's how it works. So, I think you've seen enough of that. I'll be reading from this. And I won't leave this up on the screen because, well, let's just leave it up on the screen. Okay. So the photon is purely entangled. That's a brand new statement, so it needs justification. How can you say that the photon is purely entangled? What does that even mean? Yeah. And so the images of all the universes that might be at any one instant could obtain a Schrödinger interpretation, which is the cat paradox, or else consider this. Now, if you didn't follow that, don't worry. This is an anti-paradox. That photon is everywhere on the surface of the wave, and it is still a particle. That does explain why it arrives as a particle on a photographic plate. It did not travel as a particle. I'm saying that it did. And that solves the paradox if I can prove it. So the photon is everywhere on the surface of the wave. That's superposition. That defines what superpositionality is. And now I'm going to define what entanglement is. That one proton is any photon, not proton. I do this a lot, sorry. Photon, proton, a lot of tricks of language. But a photon could arrive as a particle in any spherical direction that it's propagating in. So wherever that photon arrives, it arrives as that photon. Well, that's spooky, isn't it? Well, you can explain that by saying that the surface of the wave is the proton. The photon, goddammit, sorry. The photon. I'm dyslexic, so I do throw a fit sometimes. I get very upset with doing that. And I'm sorry, I'm retarded, okay? So it's a photon, not a proton, goddammit. And if you hear me say that and I don't correct myself, forgive me. And correct it in your own mind. You know it's not a proton, okay? So that's my rant. And blessedly brief this time, okay. So that photon is superposed on the entire surface of the wave. That is a variation of the de Broglie pilot wave theory, which was somewhat revived by David Bohm before David Bohm gave up the ship and turned to philosophy instead. And he stayed that way. One of the most amazing exponents of the philosophical solution, which he went and talked with Krishnamurti. He had conversations with the Dalai Lama, and the Dalai Lama deigned to dedicate a book which was not by Bohm, but it was about Bohm, and that's in yesterday's lecture. All right, so let's complete this so we can move on. You see the point then. What I'm saying is you can conceive of the waveform of light as consisting of, I'll just say at least a photon, but now we're getting into something really interesting. We're just going to talk about one photon, and it makes one wave. Well, that wave at the surface is the photon. That's tautological, but that's the paradox. It's not a particle. I'm saying, yes, it is. It's all those particles. And that's the multiverse. That is the many worlds. That's where the cat is alive and dead. Because that photon, as a particle, cannot be in more than one position. Oh, it's way worse than it being in more than one position. It's in every position. That defines the surface of the wave. If that can be proved, that's the solution to the entire paradox. We can then apply it to all the other forms of the paradox, which mostly concern the electron. But many of them concern the photon. That's because the photon is an electron. It's another form of the electron. The proton, does it have two states? Yes, it does. Its other state is called a neutron, and we're going to finally solve that. Why is there such a thing as a neutron? You know how closely related the photon and the neutron are? They're identical. There's no difference between them, except something that cannot be seen or measured. But it can be measured indirectly. The direct measurement from which we have to make a deduction is that the neutron lacks the proton's charge, which refers to the proton's relationship with the electron. The neutron does not take orbital shells around it. It's not exuding a force field. So the neutron is a proton. They're exactly the same measurements, with a tiny difference that has to do with the three-quark harmonic at its core. Now you can turn to the electron, which we covered yesterday, and if you don't follow me exactly as much as you'd like, look at yesterday's lecture. Because the electron is an antiparticle. This discards the entire Standard Model, not as being invalid, but just as having no real validity in reality. And the Standard Model of particle physics declares itself axiomatically at its axiomatic basis. It starts out by saying, this is bullshit. This is a bullshit system, because it says everything in the universe is a particle. So the theory itself knows that it's wrong, even if its practitioners pretend that it's right. It can't be right, because not everything in the universe is a particle. Isn't that interesting? That the Standard Model of particle physics, with its over 30 particles, I think, is completely invalid. And I'm going to leave it at that because it is. Although it could be argued quite cogently that there's something to it, there is. And that's part of the paradox. That it's completely absurd, and yet it's useful. We need to solve that absurdity. The only way to unravel the Standard Model of particle physics is, first of all, to realize that it's false. It's absolutely false. And you must take a hard line on this or you're not going to get the quantum paradox. Because the Standard Model of particle physics covers up very carefully the paradox itself with a false assumption that everything is a particle. Okay, you should accept that. If you don't get that, you're not ready for this, okay? So be cautious here. The waveform of the photon is a distributed photon, not a stretched wave. That's paradoxical, but let's go on. The photon is everywhere at once, on the surface of its wavefront. That's a variation of the de Broglie pilot wave theory, which, if you don't know what that is, it refers to the waveform, which is not a particle, but the particle kind of occupies a sink in the wave, so the particle is moving with the wave. Well, of course, that doesn't work, and that's why de Broglie was ashamed at the Solvay conference when he broached this, because everyone was trying to get at the quantum paradox at that time, before they gave up and gave in to Bohr, who just said, make money, don't worry. Einstein said, I'm not in it for money, I'm in it for understanding. you fake scientist. And Bohr flipped him off, and now Bohr won. Well, I'm reviving the conflict, because Bohr lost. So, the photon is everywhere at once. That's its transluminality at the moment of measure. That's the collapse of the wave function, is when that photon, which is infinitely number of photons on the surface, no matter how big the wavefront is, there's an infinite number of photons. There's a footnote to that. But when you measure it, all the other photons disappear, because there always and ever was just one. And that is maximally spooky. Now we're getting to right on the verge of solving this. So that's the collapse. There is now a different form of the paradox. When the electron reaches the Euler ratio radius of the proton, which you should understand, in case you're too lazy to look at the last two lectures, let me just tell you what the Euler ratio radius of the proton is. The proton exudes two forces. That's unknown right now in physics, but it has been proved. And I'm just telling you what we know about the proton. It has a force shell, a force field, that on the inside is centrifugal and on the outside is centripetal. That's unknown to physics, but that is absolutely true. So this is the beginning of getting at the quantum paradox from the inside out. Is first of all, nobody has ever defined the proton correctly. I just did. It's two forces in balance. And at a shell, and you saw I showed you, there are concentric circles that are parallel within each circle. This is analogous to the sphere, that any sphere has inside it smaller concentric spheres and outside larger concentric spheres. But there could be a pressure. The outward pressure on the sphere is called centrifugal force. That's its name. That's physics. And there's only one other force in spheric space. Centripetal. That's gravity. So the proton is the source of gravity. That has to be accepted or we can't go on. So accept it. This is a hypothetical sequence. So you have to accept what I'm saying, everything that I say, or you won't get this. Because it only comes together, it only synthesizes itself at the end. So it's kind of like a drama where you're going to only get the solution to the mystery at the very end of the movie. And then it's an aha wake-up moment. That's what you're going to get. And you're going to be one of the first humans to ever see this. The solution to the quantum paradox. All right? All right. So the Euler ratio radius is the surface of the proton. That's where the electron stops. The electron will not penetrate that shell. Instead, what it does, it occupies the shell. So you know that. Now you know what I meant by the Euler ratio. It's the radius of the proton where inside the radius is centrifugal force going out. That's redundant. And outside that radius, it's centripetal force pulling in, which only affects the electron. That's critical. So it's gravity that only the electron responds to. Is that true? Not quite. Protons cohere, but they don't willingly cohere. If you have two independent protons, they repel because they're both exerting centrifugal force. But at the center of the proton is got to be a mechanism that generates centrifugal force, which repels the other centrifugal force of the other proton. But if that limit can be penetrated such that the protons come into sufficient proximity, they'll bond. And as many as 100 or more will bond. After that, they start to fall apart by a process called fission. And it begins at about uranium. That it'll fall apart by itself. It's radioactive is what we say. So, protons will bind, but a very strange force is involved there, because normally these two particles repel. and they should not be able to touch. But if they do touch, they lock together. And that's centripetal force again. So normally the centripetality of the protonic force field only affects the electron and only affects it into a radial limit beyond which the electron will not continue to go in. It will never collide with a proton. Instead, it makes a sphere, a standing wave sphere, where the electron is everywhere in that sphere at the same time. And now you're starting to see the similarity with what I said about the photon. All right, let's go on. The electron reaches the Euler radius. It takes a curved right angle into shell formation. This curve was identified by Bošković 250 years ago. This action changes the characteristic, or one could say the state, of the electron. It changes shape. It changes radius to adjust to the presence of the proton, and that's how it does it. All right, let's go on. To the proportion that it had been a particle, it is now a wave. That's known. That's a fact. It's a wave. When it's in the atomic state, the electron is no longer a particle. I say it is. It has to be. It's either a particle or a wave at all times. Well, that's part of the paradox. We're going to now penetrate it, and this is how to get it. So let's keep going. The electron must have already possessed this wave characteristic, unless there is some change of energy state. There's not. So therefore, the electron cannot be a particle unless we can extend the concept of a particle to include this two-state object called the electron. The proton is also a two-state particle. But when it's in another state, it's a different particle. But it's the same particle in two different states. And the proton will change into a neutron spontaneously. And a neutron will change into a proton spontaneously. Much more easily, in fact. But beta decay accounts for the other inversion. This is the inversion of the quark harmonic. What we want is the equivalent of the quark harmonic for the electron. And that will be a property of a different dimension, which, since dimension is already taken in linear space, we're going to say domain. And all of this information I want you to just hold in your mind for the synthesis step, which is coming. Can we say now what the electron is, either as a particle or as a wave? See if you can answer that. If you can, you'll be the first to ever answer that. Unless, you have to exclude me, because I already know. I've got this. But you're going to get it too. All right? So there's your tantalizer. Can we now say that it's a particle or a wave? We can say this much. The manifestation of a particle in this universe has already been given. It's a proton. So we know what a particle is, because when this particle changes state, it changes into a different particle. We give them two different names, the neutron and the proton. Those are two different states of the same thing, all right? But that's in space. The electron does not exist. I'll just say this way, its primary locality is not in space. Its primary locality is in what Einstein might call time, or a relativist might call time. I'm going to show you why that's a misconception. It's because time is a concept that's already been linearized. We derive the concept of time from a phenomenon that has never yet been correctly identified with a manifestation of time. And this will end all of the philosophy and pseudo-religious, practically, harebrained ideas about time. When you understand what time actually is, it's obvious. But sometimes in science, the most difficult thing to be able to say is what is obvious. That time is linear? That's ridiculous. No, time is not linear. if it's seen correctly. But when you call it time, you've already defined it as being linear. That is the illusion, the linearity of time. But it's still part of the paradox because we know that time is linear for local time. All local time has a linear characteristic. That's what defines our ability to measure distances to stars, which is on a straight line, which we get from a spherical propagating wave. So there is a linearity, well, certainly to space, but it's also in the case of the photon that's identical with the linearity of time, and that's what time is. It's parallel to space in some sense, because when we measure distance in cosmic space in light years, you know what that actually is? It's a direct correspondence between space and time. That's why, well, let's go on. Let's complete this and maintain continuity. All right. We can now say, can we say, well, let's go on and actually say it right. Here in its particle state, okay, let me pick up where we left off. Okay, the proton is a space particle. I've proved that, so accept it, because that'll give you the definition of the electron both as a particle and as an antiparticle. The electron is a particle to the same degree that the proton is, because they both have a locality. But the electron lacks something that the proton has, and that's position. That's not locality. Locality is a generalization. We know the electron is in a certain range that we can arbitrarily narrow, but probabilistically we know where it is. But that's not the same thing as having a position. Only a particle can have a position, and that's why we cannot measure even the radius of a fermion electron. All right, let's go on. We observe this hierarchy in our interpretation of the electron here in its particle state. So we can conceive of the electron as a particle because it has a locality, but it's not a particle because it doesn't have a position, because it's a wave. Okay? That's really, to restate the paradox, it shows that it can enter another state, the shell state, in which physics has found that the particle can no longer be located except on a statistical distribution. You've heard of this. This is the exact definition of a wave. That's right. It's a statistical distribution of position. That's a wave. Therefore, certainly we can begin with the observation that the electron can transition between two states without evident loss of energy. The Bohr atom is stable for basically all eternity. A simple atom of a proton and electron is stable forever. And no matter what happens in the absorption or emission of energy, which would be light, it stays at a fixed radius and stays that way forever. And there's no loss of energy, because the only energy we know of is in the photon. That is, transmissible energy is done by a photon. Even the particle physicists tripped over this. So they have what are called virtual photons to describe every force transaction. A little bit silly, but the standard model of particle physics is worse than silly. So, this is the exact definition of a wave. Therefore, we certainly can begin with the observation that the electron can transition between two states. So can the proton. They both transition, both particles. You can call them both particles, but if you want to be more accurate, the electron is an antiparticle. And so we steal back the word that we need, because the standard model of particle physics doesn't know what they're talking about. When they say, for instance, the electron has an antiparticle called a positron, that's purely mathematical. They would argue with me to the death and they would actually win. So this is also part of the paradox, because what I said is also true. This is superpositional logic. I'm right, and they're right. And that's why this gets heated. Very heated. As in the confrontation between Tim Maudlin and Bernardo Kastrup, they called each other stupid within the first 3 minutes of what was supposed to be an hour presentation. They called each other stupid. That's how hot this gets. It's because they were both right. But when you're looking at the other side, all you can see is how the other guy is wrong. And then he's looking at you, and he can see that you're wrong. And so you end up calling each other stupid. What they should have done was figure out each one how the other one was right. And come down off of their high narcissistic horse. All right? That's my little lecture for the day. This could imply that the electron could be said to have only one state. Well, which one is it? Particle or wave? It's a wave. Accept that for now. All right. That would be consistent, and that is the positive aspect of this paradox. It is that we can perfectly describe the two-state existence of this object, but we can do so in two reciprocal ways. That is the electron. It is the reciprocality of this hierarchic inversion that produces the sensation in us of a logical contradiction in the form of a paradox. Because we're talking about two true states that seem contradictory. That is a paradox. It's a special case of a paradox, one which we've never encountered before in the entire history of physics or science, is a paradox of this form. And it is practically the definition of superpositionality. So let's go on. It is the reciprocality of this hierarchical... I can never say that right, do I? This hierarchic inversion that produces the sensation in us of a logical contradiction. A paradox is not inherently a contradiction, though. Rather, a paradox involves a different relation, a relation that is not exactly contradictory, although we do classify paradoxes that way. I've reclassified it because there are two different types of paradox, and we're dealing with a relatively unknown type of paradox. This is why it's so completely baffling, because we don't even know where to begin to solve this. Well, I do. The contrariness that arises in our minds is not the fact that something is being both true and false at the same time, but that something is being true in two different ways, each of which is sufficient. So it's kind of like the Pauli exclusion principle, which says that two electrons cannot occupy the same state within a certain proximity. That's not exactly a paradox, but then you could say, no, that exactly is a paradox, but they're kind of different kinds of paradoxes. All right, normally what we do then is compare the two ways in which the object behaves consistently. That'd be a wave or a particle. But when we go to compare these two ways, in the case of the electron, we cannot reconcile that it manifested two ways of being in two states that can't both be true at the same time. By which is meant really in the same universe. They just can't, that thing cannot be a wave and a particle. But it is, isn't it? It's exactly what it is. So which one do we call it? I'm saying for now, call it a wave, but if you are going to call it a particle, call it an antiparticle. And I've already shown you why in the last two lectures, so it's very important now to maintain continuity to get the synthesis for this. We're getting there. Let's keep going. For instance, The sun cannot rise both in the east and in the west. That's a contradiction. Okay, you see, that's not a paradox, that's a contradiction. But what if it did rise in the east and the west at the same time? Then it would be a paradox. Well, you're never going to see anything like that, so don't worry. But notice how you found out, in a quick mental evaluation, how you verified that this is a contradiction. You settled the matter with this comparison, which is that it never rises in the west, so that was easy. Now do the same thing with the definition of an electron. If you begin in any other way, other than to say that the electron has both the characteristic of a wave and of a particle, you cannot describe both valid ways in which the object changes state. Because it does change from a particle to a shell, doesn't it? Can you knock an electron out of the shell? Not only can you, it'll change shells by itself if there's an administration of energy. This does have to be precisely defined, but it is known. An electron will jump from shell to shell. And when it can't anymore, it makes a photon, not an electron. So the electron and the photon are the same particle. So you could say it's in three states. The proton doesn't do anything like this. When it changes state, it's between two particles. It's never a wave. I'm going to show you something in a moment that may blow your mind, but actually, it's important to realize that everything in the universe is energy. You've heard that stated, that everything in the universe is energy. Well, how can you say that of the proton? That needs to be answered. And that's another aspect of the quantum paradox that unexpectedly now involves the proton. Because if the proton is an energy state, which it is, it's a different kind of energy. Because it doesn't have motion. The electron is missing something to the same degree that the proton is missing motion. It doesn't manifest motion. What it does is it manifests a force field that affects motion. But the electron does the inverse. It doesn't manifest space. And that's why we can't measure its position. It's because it's not spatial. It's in another dimension. And I'm going to show you that that dimension is orthogonal to the space dimension. Einstein proved that. But he proved it on a derivative concept of, in this case, it's the antiderivative of time. What we need is the antiderivative of time, because time is a derivative concept of angular momentum, which does not take place in space, but it has a spatial characteristic to the same proportion that the proton has an energy manifestation, and these are reciprocal, and neither one has been identified. And that actually is what will lock the two aspects of the paradox into something that is no longer a paradox. But for that to happen, we must know the relationship, or we can't visualize it. That's the only way to understand something, is by visualizing it. I could give a sermon right there about how you can be deceived by numbers, but I think you already know. Notice how you found out. The electron has the character where you can't, yeah, that's right. And to wrap this up, the electron has both characteristics. Okay, if it indeed is a particle, then it can change into a wave. We could say that. It certainly appears to, but unless it had already been a wave, it could not change from particle to wave. That's another way to say it. We're not sure which way to say that. Because it has both, but how does it change from one to the other? Does it change from one to the other? Or is it always both? And we need to reconceptualize how he distinguished between a particle and a wave. The answer is in there. We're getting to it. This is the hypothetic phase to establish some sort of rule for defining the electron as a particle or a wave, but it somehow changes from one into the other without a loss of energy, and that's an hour. Here's what we're going to read next. And to close this off, to give you a much closer view of the solution to the paradox, so that eventually you're going to actually see this, and you might have seen it already. You could see it at any time now. I know this because I went through this process. All right, orthodimensionality, I showed you that. There are two dimensions, but in order to know what is meant by a dimension, you have to discard the linear notion of dimension, because it's false. It doesn't match physics. We make a grid for our numbers. We don't make a conceptual space for physics. We make a conceptual space for our mathematics. And then we impose it on the universe, which does not have that shape. It's spherical. You notice everything in here is a sphere. Everything is spherical. That's because everything is force balanced on two forces, centripetal and centrifugal. You would think those would be two opposite directions. They are in spheric space. But spheric space has two dimensions that are orthogonal. The radial line that comes out from the center is all possible lines. You can see that they're rays, though, because there's no such thing as a line in the universe. There is such a thing as a partial line called a ray, and it's a force line. And it's always based on force. Linearity in the universe is based on force. You could prove that. But when you're looking at the actual force itself, without the imposition of numbers, which are linear, and you're not looking at the linearity, you can see the integral. It's all the lines. And there's only two directions. Pulling in, which is gravity, or the effect of the proton on the electron, which is gravity. It is, and we're going to prove that. This is the unified field theorem as well. I told you this will unify everything in physics. It does. On a force balanced system that was discovered 250 years ago. So to close this up, so you have something to think about until the next lecture, which will be shortly, because I'm on a roll, as you can tell. Let me finish this. I wrote this for a reason. All right, well, you can read that. We think of the two directions in spherical space as either pulling in toward the center or going out from the center. Those have well-known names in physics. It's called centripetal force and centrifugal force. But it turns out that centrifugal force is not generated anywhere in the universe. There's no such thing as centrifugal force that we can find. Oh! Almost forgot. Yes, there would have to be a centrifugal force to balance gravity, wouldn't there? According to Emmy Noether, who won a Nobel Prize for her discovery of force symmetry, then yes, there has to be centrifugal force, since we've already identified centripetal force. It's called gravity, which is caused by the proton. Does that make sense? It better, because that's the truth. So there's the centripetal force of the universe, and it's the only centripetal force. It's based on a particle that has a center, so it can generate a force field. That's a proton. What's the electron? It has to be in a non-spatial domain. It's not in space. But that's part of the paradox, because we can find it in space. It's just that we can only find it statistically, but it's definitely there. It has state. And if it has state, it's there. But is it in space? You could say that it's in space, but how is it manifesting in space? Not with a force field. Only the proton does that, and that creates our perceptibility of space. is because of the action of the proton on space. It really generates space with a centrifugal force field beyond which it's centripetal for the atom, right? All right, so that's a proton. It's a space particle. Then the electron is the contraspace particle. And what we need now is a definition of contraspace. We know exactly what that is because I discovered it. It's the surface of the sphere. Well, obviously that's a different dimension. It shows every sign of being a different dimension because inside, well, not inside, but on that sphere, it's pure motion. It's pure motion. That's what the electron is. It's standing motion. That's not like a contradiction. Look at a spinning globe. Is it moving? No. Isn't it? Yes. It's just not moving in space. Well, what's it doing then? You could say it's spinning. That's a very, very difficult quantum number even to define, is the spin. It's something spookier than that. I'm going to show you the answer to that so that you actually know the answer to all of these enraging questions, because you'll see it. That'll be in the next lecture. Stay tuned. This is Anagalactic bringing you, well, the secret of the universe, you could say. I do say because it is. Certainly in terms of physics. In the next lecture, I'm going to give you a much deeper insight into the secret of the universe. The secret of physics that unlocks the quantum paradox and defines everything that nobody has ever been able to define because they can't see it. Because they're not using geometry. Be right back. Stay tuned and keep looking up when the sky's blue.